Today we're going to talk about the Galton Board. Invented, or at least named after, Francis Galton. What we have is a bunch of pegs and a bunch of slots. Now when I turn this over, all of these balls, 3,000 of them, will fall through those pegs and they'll scatter randomly, in the sense that we don't know where each individual ball will go. But because there are so many of them, out of chaos comes order. Look at all that wonderful, wild randomness turning into pretty much the same exact shape every single time. A normal distribution. Let's begin by talking about the pegs. The pegs on my Galton board are arranged in a triangular pattern like this. We start with one peg. Below that peg in the second row, there are two pegs on either side. The third row contains pegs arranged like this, the fourth like this, and so on. Now it's because of this arrangement of pegs that the Galton board is sometimes called a quincunx. A quincunx is a pattern of 5 objects, a certain way of arranging them, where 4 of the objects are on the corners of a square and the 5th is in the middle. You're probably familiar with the quincunx if you've ever looked at a die before. Now anyway, when the balls fall through the machine, they first reach peg number 1 in the first row. And once they do that, they have a choice. Well, they don't really have a choice, but they will either go left or right. And because of the way the Galton board is designed, there's about a 50-50 chance that any given ball will go to the left or to the right. Once that's happened, they've reached the second row of pegs, where they will either go left or right. Left or right. Now, because at each peg a left or right bounce is equally likely, in the long run, across a large number of trials, we expect balls whose complete paths contain about the same number of left and right turns to be the most common, which means we expect more balls to wind up pretty much right below where they started, and many fewer on the edges, which corresponds to having way more of one kind of bounce than the other. We don't know where any individual ball will wind up, but we can say something about how they will all behave. Now, the actual probability that an individual ball will fall into any one of these slots follows what is called a binomial distribution. But there's a nice thing in mathematics called the central limit theorem, which tells us that under a large number of trials with a large number of objects, like 3,000 balls, a binomial distribution approximates a normal distribution.